GSAP is a space-based capability that collects space situational awareness data, allowing for more accurate tracking and characterization of human-made orbiting objects. The satellites have unobstructed and distinct vantage points for viewing resident space objects orbiting Earth, without the weather or atmospheric disruptions that limit ground-based observations. This will be the third launch for the GSAP program, following the successful 2014 and 2016 launches of AFSpace 4 and 6, which both launched atop Delta IV rockets. USSF-8 will be the first flight of the Atlas V 511 configuration. Stay tuned after liftoff to hear from our USSF-8 mission director, Colonel Erin Golden, where she will highlight the criticality and diversity of our space partnerships that are required to achieve mission success.
ULA's Atlas V 511 rocket, the first and only planned mission using this configuration, is launching USSF-8. This is the 91st Atlas V launch and ULA's 140th launch. Built in ULA's 1.6 million square foot production facility in Decatur, Alabama, the Atlas V Common Core booster is powered by an NPO Energomosh RD-180 engine and a single Northrop Grumman solid rocket booster to provide additional thrust at liftoff. The Centaur second stage is powered by an Aerojet Rocketdyne RL-10 engine. The two spacecraft are encapsulated in a 5-meter diameter Ruag payload fairing. These rocket components travel from Alabama to Cape Canaveral on ULA's rocket ship. Once in Florida, a series of events led to today's countdown. Here's ULA's Isaac Spence to take us through that process.
Thanks, Caroline. I'm here at the Vertical Integration Facility at Space Launch Complex 41. Behind me, the team is preparing to move the Mobile Launch Platform, or MLP, to the pad. Before we do that, here's a look at how the rocket was stacked. Our process began with lifting the 107-foot or 33-meter booster onto the MLP. Then the team mated the SRB to the booster, followed by the transport and lift of the Centaur into position. Finally, the payload fairing, with both spacecraft already encapsulated, was mated to the Atlas V rocket. Once the rocket is fully assembled, we start the countdown procedure by moving the mobile launch platform from the vertical integration facility to the pad. To complete this move, 6 components are used for the 20-minute trip to pad, which spans about 1/3 of a mile. The MLP weighs approximately 2 million pounds, supports the rocket, and contains air conditioning, electrical, and commodities lines. The undercarriages bear the weight of the MLP and the rocket. Additionally, 2 rail cars lead the move, with the payload van providing spacecraft communication and the ground van providing support for the rocket. At the rear of the convoy is an environmental control system providing air conditioning to the payload and rocket, and trackmobiles power the nearly 3 million pound convoy. The Atlas V rocket stands 196 feet, or about 60 meters, and weighs 775,000 pounds, or more than 350,000 kilograms, fully fueled. With the rocket on the pad, the launch team then transitions to fueling and other final preparations.
ULA's Atlas V 511 rocket is launching both GSSAP spacecraft to near geosynchronous orbit. Let's learn more about today's flight.
Liftoff of the United Launch Alliance Atlas V rocket.
The RD-180 main engine and 1 solid rocket booster ignite to lift the Atlas V rocket away from the pad. Together, the main engine and single SRB generate a combined liftoff thrust of 1.2 million pounds, or 5.3 meganewtons. Shortly after liftoff, Atlas begins a pitchover to attain the proper flight path while minimizing the dynamic pressure the vehicle experiences during flight. The Atlas V reaches Mach 1, the speed of sound, at 58 seconds. 2 minutes into flight, the GEM 63 solid rocket booster is jettisoned. During ascent, the spacecraft are protected inside a 5-meter diameter payload fairing. At approximately 3 minutes 30 seconds, the rocket has climbed above the densest part of Earth's atmosphere, and the payload fairing is jettisoned. At 4 minutes 21 seconds, propellant levels are depleted and the main engine shuts down. 6 seconds later, the Atlas Centaur separation system activates to release the booster stage. The vehicle now weighs a little more than 5% of what it did at liftoff. At 4 minutes 37 seconds, the first Centaur main engine burn begins. Over the span of more than 6.5 hours, Centaur's RL-10 main engine will perform 3 engine burns. Approximately 6 hours, 31 minutes after liftoff, the RL-10 engine ignites for a final burn. This burn enables Centaur to make a plane change towards its geosynchronous separation orbit. Nearly 2 minutes later, Centaur completes its final engine cutoff, following a guidance-commanded shutdown, a capability which ensures precise orbit injection. 6 hours, 35 minutes, 48 seconds after liftoff, Centaur releases the first satellite, followed by the second satellite, approximately 10 minutes later. The Space Force's identical Geosynchronous Space Situational Awareness Program satellites then continue their journey to geosynchronous orbit.
As I've mentioned, this is the first and only planned Atlas V 511 configuration. It is the only unflown configuration of the Atlas V family. Here's ULA's president and CEO, Tori Bruno, on why this unique rocket is right for today's mission.
Hi, I'm Tori from ULA, and I'm here to talk to you about our upcoming mission, USSF-8. This is a really cool mission. We're going to launch 2 spacecraft directly injected to a high-energy, near geosynchronous orbit. And a lot of you have asked about the configuration of the rocket that we're going to use. Well, this will be the first flight of the big slider, the Atlas 511, with only 1 solid rocket motor. And we call it the big slider because if you watch the launch, you're going to see a kind of power slide off the pad because of this asymmetric torque. And a lot of you have wondered, well, how do you fly that? Well, that nozzle is canted to pass through the average center of gravity, and the RD-180 has tremendous control authority with its thrust vector system, and it can overcome that and compensate for it. And this is just the right amount of energy to carry these 2 payloads to their very cool mission of space surveillance, kind of like a neighborhood watch for GEO. Go Atlas, go USSF-8.
Today's flight is dedicated in memory of Northrop Grumman employee James Jim Mooney. Following a 20-year career with the U.S. Air Force, Jim joined Orbital Sciences Corporation in 2004. As a spacecraft integration and test department manager for Northrop Grumman following their acquisition of Orbital Sciences. Jim oversaw the complete assembly, integration, testing, and launch site operations for numerous commercial and military spaceflight vehicles. This distinguished path led to his assignment as the overall production, integration, and launch space manager for the GSSAP program. Jim's leadership and dedication to the mission was a driving force behind the successful production and launch site integration of 6 state-of-the-art GSSAP spacecraft. For this dedication to his family, friends, coworkers, the mission, and to the security of our nation, we are eternally grateful to have crossed paths with Jim and to call him a friend and patriot. We remain in the planned 30-minute hold as we continue towards liftoff. In a few moments, launch conductor Ron McKee will poll the launch team for the final go to pick up the countdown. 29 engineers and managers are polled for system status and readiness to proceed. This is the final status check for all Atlas vehicle systems, ground systems, spacecraft, and the U.S. Space Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Ron McKee performs the final polling.
Out minus 7 minutes.
Status check to proceed with terminal count. Atlas systems, propulsion.
Go.
Hydraulic.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
GC cube.
Go.
Operation support.
Go.
Com.
Go.
Umbilical.
Go.
ECS.
Go.
Red line monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle systems engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicle is ready to launch.
Mission director.
You have permission to launch.
Proceeding with the count. ALC verified T0 set for 1900 Zulu.
Verified.
Polling is complete. The ULA launch team and the Space Force mission director are go for launch. From T-minus 4 minutes until launch, you will be listening to Ron McKee and his team performing the final steps in the countdown procedure. Several critical activities occur in the final minutes before launch, including verifying fuel tank levels and pressures in the booster and Centaur and arming the flight termination system. At T-minus 25 seconds, you'll hear Go Atlas, Go Centaur, Go USSF-8. This is the final status check of Atlas, Centaur, and USSF-8 readiness. At T-minus 3 seconds, the main engine ignites, followed by ignition of the solid rocket booster. Then, after seeing Atlas V lift off the launch pad, you'll begin hearing flight commentator Patrick Moore providing launch vehicle ascent data. This is Atlas Mission Control at T-minus 4 minutes and holding. We anticipate releasing the hold in just a few moments.
On my mark, the time will be T-minus 4 minutes. Count. 3, 2, 1. Mark. 3:55.
Ground pyros enabled.
The countdown clock has resumed and we are go for launch at 2 p.m. Eastern. With liftoff approaching, we're going to raise the volume on our launch team so you can hear the final preps taking place.
.310.
LC spacecraft going internal.
Roger.
.3 minutes.
Securing LO2 talking.
Atlas tanks to flight pressure.
250.
FPS internal.
.210.
LC spacecraft internal.
Roger.
.159.
Vehicle internal.
.155.
Launch sequencer start.
.150.
Securing Centaur LH2.
Securing Centaur LO2.
.140.
Launch enabled.
.137.
FTS arm.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and eastern range are go for launch.
120.
With the use arm. FCS count started.
115.
Reduce ECS for launch.
Roger. 110. Bin valves locked. One minute.
T-minus 1 minute.
Range green.
Seconds.
Stable at step 3.
$28. 25.
Status check.
Go Atlas.
Go boost Centaur. Go USSF-8. ECDS
Minus
reduce for launch.
10, 9, 8, 7, 6, 5, 4, 3. We have ignition and liftoff of the United Launch Alliance Atlas V rocket carrying SF-8 for the United States Space Force.
Now 10 seconds into flight, vehicles begun the pitch over maneuver, body rate response look good.
You're now hearing the voice of Patrick Moore providing launch vehicle ascent data.
Now 20 seconds in, RD-180 propellant utilization system has gone to closed loop control system response looks good. Now passing 30 seconds into flight. Vehicles completing the pitch over maneuver, body rate responses continue to look good, engine operating parameters continue to look good. SRB chamber pressure within expected ranges. Now coming up on 58 seconds into flight, Mach 1, Atlas 5 is now supersonic. RD-180 engine operating parameters continue to look good. SRB chamber pressure looks good. Now passing through max Q, maximum dynamic pressure. Body rates continue to look good throughout boost phase. Now 3 minutes remaining in the booster phase of flight. Now passing 1 minute 30 seconds into flight. SRB chamber pressure tailing off now as SRBs are burning out. And we have SRB burnout. RD-180 throttling down slightly as expected. Engine response looks good. Now passing 1 minute 50 seconds into flight. Body rates continue to look good throughout boost phase. RD-180 engine operating parameters continue to look good. Now 2 minutes into flight, we have good indication of jettison of the SRB. The Atlas V now weighs 1/2 of its liftoff weight. And vehicle's gone to closed loop steering. Body rates look good. Two minutes remaining in the booster phase of flight. Atlas V is now 38 miles in altitude, 35 miles downrange distance, traveling at 4,200 miles per hour. Now 2 minutes 40 seconds into flight. RD-180 pump speeds and injector pressures continue to look good. Body rates continuing to look good throughout boost phase. Now passing 3 minutes into flight. And Centaur reaction control system is now pressurizing to flight levels. RD-180 now throttling down to maintain a constant 2.5 G acceleration limit. Engine response looks good as it's maintaining that 2.5 G acceleration limit. Now 1 minute remaining until MIKO. And standing by for payload fairing jettison. And we have good indication of payload fairing jettison. And we have CFLR jettison. Now 3 minutes, 50 seconds into flight. Body rate's continuing to look good. And RD-180 now throttling to maintain a constant 4.6 G acceleration limit. And we've begun boost phase chill down. And standing by for booster engine cutoff shortly. And we have MIKO booster engine cutoff standing by for stage set. We have good indication of Atlas Centaur separation. We have pre-start on the RL-10. We have ignition and full thrust on the RL-10. Chamber pressure looks good. Body rates look good. And this first burn of today's mission will last approximately 8.5 minutes. Now passing 5 minutes into flight. Centaur's gone to closed loop steering. Body rates continue to look good. And the RCS system has begun initial thruster firings for thermal conditioning as expected. Centaur is now 140 miles in altitude, 420 miles downrange distance, traveling at...
This is Atlas Mission Control at T plus 5 minutes and 25 seconds. We just heard flight commentator Patrick Moore confirm the successful completion of the early phase of today's flight, and all systems continue to operate nominally. Our next event, Centaur main engine cutoff, will occur in approximately 8 minutes. Earlier this week, Patrick Moore shared a little insight about his role as flight commentator and the vital information he relays to the launch team post-liftoff. Let's take a look.
Hi, my name is Patrick Moore. I'm a systems engineer in the Chief Engineer's Office at ULA, and I'm also your flight commentator for USSF-8. So my job as flight commentator is I'm taking a look at the screens here. I have some plots and schematics, and I'm also looking at the video on the wall. And so what I do is, as we're lifting off, I'm looking at the video, confirming that what I'm seeing on the screens are consistent. And then I'll start taking a look at the data in the plots and the schematics. And so my job as flight commentator is I'm looking at the data that I see here, and then I'm talking about it over the broadcast and on the net. And so the folks at ULA will be listening to my commentary, and so we have engineers that cover all different disciplines: avionics, structures, thermal, and many others. And so what they're doing when they hear my commentary is it just kind of helps give folks perspective of where we are in the launch and what's coming up. So an engineer will be looking at their specific system and all the different things that are going on with what's specific to their hardware in flight. And so my commentary helps tell them, okay, something's coming up that I might need to look at, or I should expect to see a change in my data in a certain way. And then obviously my commentary goes out to folks around the world watching the ULA broadcast. And so my job as flight commentator for them is to help provide some perspective of what they might be seeing on the broadcast and on the video to just help kind of pull everything together. So one thing that's interesting about flight commentary, when we have the rocket in flight, we're getting thousands of different measurements that we can select from, and they cover all different things from top to bottom of the rocket. So our job as flight commentators is we want to pick maybe 40 or 50 different measurements that give us an indication of how the vehicle is doing in general. We look at that in the plots here and in the schematics, and that really gives us more of a general feel that the rocket's doing well in flight, and then it's the job of the rest of the engineers throughout Denver that they're looking at much more specific measurements, like a temperature on an avionics box, or a pump speed in the engine, or things like that. And so we may not look at those, but we want to look at maybe general indicators that tell us that the whole system is doing well. So I certainly get a little bit nervous before every launch. I've been doing this flight commentary for 4 years and about 12 launches, and I think I get nervous every time. I thought it would go away, but it doesn't. So I get really excited. There's a lot of adrenaline going, especially in the last couple of minutes before launch. And I think one of the challenges of being flight commentator is you have to, kind of live within that adrenaline, but also talk yourself down a little bit and stay focused on reading the data and talking over the net. And sometimes it's a little bit of a challenge, but it's always exciting. So for USSF-8, there's no difference in how I feel leading up to this launch. I'm really excited and can't wait.
Approximately 4 minutes now remaining in the burn.
We are about 4 minutes away from MIKO 1. While we wait, this year, ULA's interim cryogenic propulsion stage will launch atop NASA's SLS rocket. ICPS will be carrying the Orion capsule to orbit. Let's hear the latest updates on this program from ICPS Avionics Lead Engineer, Joven D. Herrera.
Hi, my name's Joven D. Herrera. I'm the avionics lead on ULA's Artemis program. Our whole team is excited to be part of America's journey back to the moon. ULA is working collaboratively with the Boeing company to supply the interim cryogenic propulsive stage, ICPS, for the Artemis 1, 2, and 3 missions. The ICPS is a modified Delta IV cryogenic second stage that is the second stage of the SLS rocket. This week, we are conducting program-specific engineering testing. This is a collaborative test with the whole SLS team to ensure all of the hardware powers on nominally and the vent and pressure systems respond appropriately. ULA is managing the ICPS power during this test. The Tiger team is a dedicated team on console that will support NASA's launch team. We work closely and collaboratively to monitor all aspects of ICPS during pre-launch and in flight. We are so excited to be playing our role and returning back to the moon.
Now passing 11 minutes into flight, just over 2 minutes now remaining in the burn. Centaur systems all continue to perform nominally throughout the burn. Seeing good stable pressures on the RL-10. Body rates remain stable. Thruster activity continuing as expected.
This is Atlas Mission Control at T plus 11 minutes and 54 seconds. We are now approaching main engine cutoff 1. Let's listen in.
Passing 12 minutes into flight. Approximately 1 minute now remaining until MIKO. Centaur is now 200 miles in altitude, 1,960 miles downrange distance, traveling at 16,350 miles per hour. "30 seconds now remaining until engine cutoff. RL-10 operating parameters continue to look nominal. Body rates remain stable, now about 13 seconds until engine cutoff. PU's gone to open loop in preparation for MIKO. Standing by for cutoff. And we have MIKO.
This is Atlas Mission Control at T plus 13 minutes and 20 seconds. Patrick Moore just reported the successful completion of the first of 3 Centaur engine burns. Centaur is now coasting over the Atlantic, but we still have a long way to go. The 2 US SF-8 satellites are scheduled to separate from Centaur into a near geosynchronous orbit in about 6.5 hours. Before we leave you, here is US SF-8 Mission Director Colonel Aaron Goulden discussing the criticality and diversity of our space partnerships and how they contribute to mission success.
It's truly an honor and a privilege to have served as your mission director and to be part of this amazing team that's delivering our space situational awareness payloads to orbit. Our space capabilities, they touch every facet of our lives. They advance our understanding of the universe. They allow us to see our world with greater clarity, more accurate navigation, stronger global commerce and communications. They enable precision farming and agriculture. And overall, they just allow us to operate with greater assurances. So your Space Force Guardians, we protect those assurances and our freedom of action in space. We're pathfinding innovative and resilient new space capabilities, but we don't do that alone. We work across strong allied partnerships, sister services, and our industry teammates to do so. So you remember when you were young and you looked up at the vastness of the stars in the sky? It was inspirational. The idea that space, it represented the unknown, that opportunity to dream and feel as though we could be part of something so much bigger than ourselves. It inspired our imaginations. But those of us who are dreamers, we're not just engineers and scientists. We're extremely skilled craftsmen, trade technicians, and others that build our rockets and our spacecraft. We're journalists, business and financial specialists, doctors, lawyers, contracts experts, logisticians, program managers. We are a mix of diversity of thought, perspectives, and expertise that all come together within the space enterprise. And today, it's truly my colleagues that keep me inspired. They're uniquely talented and a truly committed industry, government, and civil partnerships that we've built a foundation of teamwork and trust that is vital for us to stay competitive across the domain and continue to champion the safe and responsible use of space. Our bold and ambitious national space missions continue to show us that our future's truly unbounded. We're creators, we're innovators, we're leaders. And it's such an exciting time to be part of this evolving industry. There's an incredible amount of opportunities across so many disciplines to be a part of it. I am so proud of each and every member of our USSF-8 team. But I said there's so much more we can do. I challenge us all to keep dreaming, keep innovating together, and never let anyone turn our stars into a ceiling.
I'd like to thank Patrick Moore for his participation in today's show, as well as Brian Sizek from Space Launch Delta 45 Weather. You can stay updated on today's long ascent with ULA's live blog at ulalaunch.com or join the conversation on Twitter and Facebook. I'm Caroline Kirk. Thanks for joining us today. Before we leave, we'll take another look at liftoff, which occurred at 2 p.m. Eastern Time.
Go USSF-8. ECDS reduced for launch.
10, 9, 8, 7, 6, 5, 4, 3. We have ignition and liftoff of the United Launch Alliance Atlas V rocket carrying SF-8 for the United States Space Force.
Now 10 seconds into flight, vehicles begun the pitch over maneuver. Body responses look good.
You're now hearing the voice of Patrick Moore providing launch vehicle ascent data.
Now 20 seconds in. RD-180 propellant utilization system has gone to closed loop control system. Response looks good. Now passing 30 seconds into flight.